Hi, welcome back. I'm Professor Ronald Vincent M. Santiago, and today we'll be discussing Module 7, which is the development of sequence networks. What are sequence networks? Sequence networks are single-phase equivalent circuit composed of the impedances to current of any one sequence only. The sequence network includes any generated EMF of a particular sequence. Sequence network carrying the currents IA1, IA2, and IA0 are interconnected to represent various unbalanced fault conditions. Now, let us consider the shunt fault point. The system is said to be balanced with regards to the impedances except at one point called the fault point as shown in the figure. We have there a three-line diagram or a line A, IB, line B, and line C given, wherein there is a fault point at one point in the system. Fault MVA. What is a fault MVA? The short circuit current at any point in the power system is generally expressed in terms of a fault MVA. And by definition, the fault MVA is equal to the square root of 3 multiplied by the nominal line-to-line voltage in kilovolts and the short circuit current in kiloamperes. And note that the Thevenin voltage is equal to the KVL, the nominal line-to-line voltage, multiplied by 1000 divided by the square root of 3. And the Thevenin voltage, noting that that is equal to the Thevenin voltage divided by the short circuit current. So from there and the previous equation, we can now get the Thevenin impedance to be equal to the nominal line-to-line voltage divided by the square root of 3 divided by the short circuit current multiplied by 1000. And that gives us to be equal to the nominal line-to-line voltage divided by the square root of 3 divided by the short circuit current Ka. So from the fault MVA, we get the short circuit current to be equal to the fault MVA divided by the square root of 3 divided by the nominal line-to-line voltage. So substitution, we can now solve for the Thevenin impedance. So that gives us the square of the nominal line-to-line voltage divided by the fault MVA. Now, to give an example about this fault MVA, we have here a three-phase fault with a fault MVA of 138 kV. Bus is given to be 5975. Find the positive sequence representation of the system at the bus. So first, we need to calculate the Thevenin voltage, and that gives us the nominal line-to-line voltage times 1000 divided by the square root of 3. So by substitution, so that gives us 79,674 volts. And solving for the Thevenin impedance, so that gives us the square of the nominal line-to-line voltage divided by the fault MVA. So that gives us 3.19 ohms. So the diagram now shows a series connection of the Thevenin voltage in series with the Thevenin impedance. Now, sequence networks. When the system is faulted, currents and voltages will contain positive, negative, and zero sequence components. The ratio of a sequence voltage to its corresponding sequence current represents a sequence impedance. So thus, the unbalanced power system can be replaced by three sequence networks, namely the positive sequence network, the negative sequence network, and the zero sequence network. Now, to illustrate further, the Thevenin equivalent of the power system at the faulted point is called the sequence network. So we need to represent a simple representation of the entire system on a faulted point with respect to the ground. The positive sequence network is equal to the series connection of the Thevenin voltage and the positive sequence impedance based on the faulted point and the reference bus. So thus, our voltage BA1, the positive sequence voltage at the faulted point, is just equal to the Thevenin voltage minus the positive sequence current flowing through that Thevenin equivalent multiplied by the positive sequence impedance. Whereas for the negative sequence, that is composed only of the negative sequence impedance measured at the faulted point and the reference bus. Notice that there is no Thevenin voltage. So thus, our negative sequence voltage BA2 is just equal to negative IA2 multiplied by the C2. And for the zero sequence, similar with the negative sequence, there is no Thevenin voltage present. But the impedance there is the zero sequence impedance measured at the faulted point and the reference bus. So thus, BA0, the voltage measured at the faulted point and the reference bus for the zero sequence network, that is BA0, equal to negative IA0 multiplied by say 0. Now, some key points to ponder with respect to these sequence diagrams. So, generators only produce positive sequence voltages, therefore only the positive sequence has a voltage source, as shown in the diagram. During a fault, the positive sequence impedance is approximately equal to the negative sequence impedance and approximately equal to the direct axis synchronous reactance. The zero sequence impedance is usually substantially smaller. The value of Cn, the neutral impedance, depends on whether the generator is grounded. Now, the positive and negative sequence diagrams for transformers are similar to those for transmission lines. The zero sequence network depends upon how the transformer is grounded and its type of connection. And the easiest way to understand is a double Y-Y. In that diagram, we have a Y-grounded Y, and that is both on the primary and secondary side. So thus, the equivalent network of that will just be a connection between A and A prime. Our CO, the zero sequence impedance of that transformer, will be connected to terminal A and terminal A prime. So meaning there is a flow of zero sequence current from the primary to the secondary of the transformer. Now, if a circuit is Y connected with no connection from the neutral to ground or to another neutral point in the circuit, the sum of the currents flowing into the neutral in the three phases is zero. Since currents whose sum is zero have no zero sequence components, the impedance to zero sequence current is infinite beyond the neutral point. This in fact is indicated by an open circuit in the zero sequence network of the Y connected circuit and the reference bus. So in that diagram, we have a Y connected transformer that is not Y grounded. So we can say that the zero sequence impedance of that transformer is just hanging. Now, if the neutral of a Y connected circuit is grounded through zero sequence, a zero sequence connection is inserted to connect the neutral point and the reference bus of the sequence transformer. So notice that the neutral point of the transformer is grounded. So we'll now have an equivalent circuit wherein the zero sequence impedance of that transformer is connected to the reference bus. Now, if the impedance is inserted, that is Cn, is inserted between the neutral point and the ground of a Y connected circuit, the impedance of a 3 Cn must be placed between the neutral and the reference bus of the zero sequence network. So aside from the C0 of that network, the Y-connected network, we need to insert twice the value of the neutral impedance going to the reference bus. Now, if the connection is in delta, the there is no path wherein a zero sequence current will be flowing to the line, the Thevenin equivalent will just be equivalent to both sides of the transformer. The say O will be connected to the reference bus. So thus the zero sequence network is opened in the delta connected circuit. So these are the different cases wherein zero sequence equivalence of a three-phase transformer. So this shows the illustration how these configurations will be, how it is connected to the circuit. That ends our module 7, and see you in the next module.